So I'd like to remind you of where we started this semester. We introduced single variable calculus and analytical geometry. The introduction included there are two branches of calculus that we study, the differential branch and the integral branch. And they each can be interpreted geometrically to answer two fundamental geometric questions, of which there are a variety of applications. The first of those questions is, what is the slope of a line to a continuous function at a singular point on that function? We've looked at this question quite in depth this semester through the derivative and saw many applications for the derivative. The second geometric question is, what is the area of a bounded region, a two-dimensional bounded region? It can be a generalized region, and we can generalize it in this way. We can define a function over the x-axis bounded by an interval, let's say between a and b. Can we tell what is the area of this region? It doesn't have a shape that we are particularly familiar with, but we can break it up into a bunch of little geometric shapes that we can then calculate the areas of and take the sum of those areas. And that is the technique in integral calculus, geometrically interpreted as the area of a bounded region. And the applications are there are many applications for what integrals can do for us. This is where we started at the beginning of the semester. We talked about what sequences are, an ordered set. We developed, we created sequences of slopes of secant lines when we were getting ready to investigate the derivative, right? So we would find the slope of a secant line, and then we would move the points closer together and find the slope of the next secant line. We would keep one of the points fixed, move the other point closer to the fixed point, and find the slope of the next secant line, and that would create a sequence of slopes of secant lines. And then we say, well, what happens if we were to try to push these 2 points as close as possible to each other without allowing them to actually reach each other? And that's where we introduce the idea of the limit. And the result geometrically from that is that the secant lines on a nice, smooth, and continuous curve, those secant lines would be approaching the tangent line. And the slope of that tangent line would be, in fact, the limit of the sequence of slopes of the secant lines. So we had sequences, we had limits, and we defined the derivative as the limit of a sequence. The limit of the sequence of slopes of secant lines, which is geometrically the slope of the tangent line. And analytically, we are saying that the limit of the average rates of change for a function would be the instantaneous rate of change. That is the limit as we allow the interval over which we're looking at to shrink. All right, so if we started with 2 points separated on the curve, but we push those points closer and closer together without allowing them to equal each other, we would investigate instead the limit of the sequence we are investigating, and we would say that that limit, if it existed, was the instantaneous rate of the change of the function. And then we did lots of applications. Well, now we are moving into integral calculus. We've introduced what the antiderivative is, and we'll see soon enough that there is a connection between antidifferentiation and the area under the curve. And we're going to start to see that idea develop in this section. And this section is about areas and distances. So here we are in section 5.1. We are relating where an application of areas under a curve we'll be looking at here will be to interpret them as distances. That's if we are finding the area under a velocity curve over a time interval, we can interpret that area as a distance. Okay? Why is that? Well, recall with uniform motion, that's where you have unchanging speed over a time interval. Okay, so that's where r is a constant rate, okay, a constant rate of change. Okay. Then distance is equal to rate times time. Okay, a manipulation of this formula, if we say wanted to find the rate of change, r, in this formula, okay, r would equal distance divided by time. So for example, if we were looking at a function that was a position function, okay, so let's say s is equal to f of t. That is a position function. Okay? If we were to take a difference in two distances, let's say this is s1 right here, okay, and then s2 right here. Okay, the difference in two distances would be a distance over a time interval, right, t1 and t2. Right? What are we calculating? We have s2 minus s1 over t2 minus t1, interpreted geometrically as the slope of this secant line. That would be interpreted distance over time as an average velocity, okay, over the time interval, the closed interval from t1 to t2. We found an average velocity. And then we applied a limit to this as we pushed one of these time values towards the other one, and then we were interpreting that the slope of the tangent line as the instantaneous rate of change. Right? We are interpreting this as uniform motion. Now, the motion on this position function is not in fact uniform, though. The velocity is actually changing. How do we know that the velocity is actually changing here? Well, we know how to read a curve now in terms of its derivative. If we take a look at the slope right here, the steepness of the slope and whether it is angled upward or downward, okay, tells us about how fast this object is moving and in what direction. So for instance here, whatever that speed is, it's a positive speed here, a positive velocity, but it's also a positive velocity here, but less, right? It's going more slowly. Okay, so relatively, at this point right here, it's going relatively faster. The object is moving at a faster velocity than it is at this point. Okay, it's slowing down because the slope is closer to zero, and then it increases in velocity again. So note that as we know now by use of the derivative and analyzing the shape of this curve, note that actually the velocity here is not constant on our interval from t1 to t2. So what we're looking at here when we are taking the difference in the distances divided by the difference in the times over the interval is not an actual account of the velocity, but is instead an approximation for the overall velocity for the time interval. It is an average velocity. So we have done an extreme simplification here by this design. We did not have uniform motion. Uniform motion requires that the rate of change is constant. Geometrically, we know if the rate of change is constant, then we must be along a line, right? A linear function. That's the only function that truly has a constant rate of change. But this instead is a function that is nonlinear. If we shrunk this interval down enough, if we put t1 and t2 close enough to each other, we would find that for that small instant in time, just for that small little interval of time, that the velocity within that interval was pretty much constant. Right? It wasn't changing fast enough. Eventually we can create a small enough interval where the velocity doesn't change fast enough on that interval that we could reasonably assume that it is constant for that interval. Okay, now let's take a look at the distance. All right, right, solving this formula for distance and how we can interpret this instead, right? The velocity was interpreted as a ratio here, a division process. We divided position by time to get velocity. What do we do if we wanted to find distance? To find distance, we can take a velocity and multiply that by time. So now let's consider this example. What is the derivative of the position function? The derivative of the position function we know to be the velocity function. Right now, I'm not going to necessarily draw what is the velocity for this position function. Instead, I want to keep a nice quadrant 1 but velocity function. Let's say that we have, let's say that we have some function here, okay, that is in fact a velocity function. Okay, so y is equal to v of t, a velocity function, right? So the output of this function would be telling us the rate of change, right? The speed of an object, right? If we took, let's say, 2 values of velocity off of here, all right, so call this v1 and call this v2, then we have like a change in velocity happening there. Okay, when we put that over a time interval, t1 and t2, well, let's not go back to the question of what is the slope of this of the line between these two, because that would be the rate of change. That's acceleration. That was a different question. But what if instead we asked this question? What if we were to choose anywhere within this interval? We could in fact choose this point here, or this point here, or any other point along the curve between these two. We just need a sample point. If we take some sample point within there, that would give us a representative velocity, just a representative of this time interval. Well, I'm going to name this velocity here. I'm going to give it a special name. I'm going to call it v with a star up here. Okay, it's our star value. I'm selecting that particular velocity within this interval. And again, we didn't have to choose it to be like in the center here. We could have chosen it to be any point within this region. For context here, let's say that you're driving a car and you have the option to look down at the speedometer at any moment that you want to see how fast you're driving. But when you're driving the car, you're not likely to be staring at the speedometer the whole time. You should be looking at the road. So let's say you have a time interval. Let's say over a minute, or let's say a minute is passing. Let's say from 12 o'clock to 12:01 on some day, right? While you're in a car, you're driving or someone else is driving. Between 12 o'clock and 12:01, at some point during that minute, you glance at the speedometer and you say, well, that's our current speed. And then you look away, but you only are allowed to look at it for a moment just to read the speedometer, and then you can't look at it for the rest of the time. That reading that you took is the representative velocity for that entire time interval now. Right? Because it's the only time that you actually observed the speed that the car was moving within that time interval. It's your representative for that time interval. If you looked at it at 12 o'clock, then you're choosing this as your velocity, as your star velocity. This one over here. If you looked at it at 12:01, you're choosing this v value as your velocity. And if you looked at it somewhere between 12 o'clock and 12:01, somewhere in the middle, right? It is your representative velocity. Now, according to this formula right here, d is equal to r times t. If we take a velocity, right, which is the rate of change right here, and if we multiply it by the amount of time we are traveling at that velocity, we would get a distance. Right? So again, if we take our v star, which is our approximation for the velocity, and if we multiply it by the total amount of time we are at that velocity. Now, in actuality, if the velocity is continuing to change, we're really only at that velocity instantaneously. But we are assuming that it is going to be our velocity constantly throughout this interval. Okay, so I'm drawing an approximating line here. There's a flat line to say that this is our approximation for the velocity throughout this entire interval right now. If we multiply that velocity by our entire time interval, that is v star times delta t for that interval, what are we finding here? We have a velocity times a time. All right, a velocity times a time. And a velocity times a time is going to give us a distance. Geometrically, though, what have we found here? We've multiplied velocity times time interval. Geometrically, what we've done is we have multiplied where velocity star is the height of this rectangle that we're looking at here, and delta t, well, delta t is the width of this rectangle here, right? Delta t is this width, and v star is this height. And we are calculating the area, right? The area of this rectangle here. Okay, so the area of that rectangle right there is an approximation for the distance that we've traveled. If the function that we're finding the area under is a velocity function, right? If we find the area under a velocity curve over a time interval, that area is interpreted as a distance. Now, there's a link here in differentiation. First off, these are interesting exercises in terms of the geometry. We have the slope of the line over here, the slope of a curve over here instantaneously, right? And we have the area under a curve over here, right? Just as over here, right, we would do a limiting process here to get the instantaneous rate of change. If over here, if we were able to shrink these rectangles down, shrink down the time intervals, let's say you looked at the speedometer every second from 12 o'clock till 12:01. That is, you looked at it 60 times. And within each one of those little intervals, you glanced at the speedometer and we took the associated velocity within each interval. And for each one of those measurements that you took, you constructed a little rectangle, right? So you did the same process, just shrunk it down like a limiting process here, right? You would find the area of each one of those rectangles represents a little amount of distance that you've added to your journey for each one of those intervals, right? And if you were to add up the areas of all those little rectangles, you would get an approximation for the total distance you would have traveled over this time interval. Because the area under this curve, from whatever the initial point is here, let's call it A, to this final point out here, if you were to take this total area here, right, if we have that the curve is a velocity curve and it's over a closed interval A to B, then that area would not be an approximation, but that would be exactly equal to the distance traveled over the interval AB. All right, now, theoretically, this means that we are looking at the speedometer at every instant of our journey. Right? We have to do that in order to create enough rectangles that are skinny enough so that we can add up all their areas and get exactly the area under this curve. Because look at the area of our rectangle here. Does that rectangle, is that really the same as the distance we actually traveled? It's not. It's actually an approximation. Okay? This is actually an approximation. Right? We are calculating a distance here, but that distance is not the exact distance that we traveled. That distance is based off of an assumption that we made. And the assumption is that the moment that we looked at the velocity on the speedometer, that velocity was going to be the velocity for the entire time interval. Okay? But it wasn't necessarily the velocity for the total time interval. It was the representative value that we used for that time interval. So we are approximating the area under the curve, and that area under the curve represents the distance. Okay, as long as we're dealing with a velocity function. Now the connection to differentiation. Again, the derivative of position is velocity. Right? We know the derivative of the position function is going to give us the velocity. Isn't it also true that the antiderivative of velocity gives us position? Right? The reverse of that process, and we studied antiderivatives just now, right? Just recently. The antiderivative of velocity is position. Position in this equation is represented by distance. This seems to suggest that we can find the distance. If we're looking at a velocity curve, we can find the distance, that's a change in position, through the use of an antiderivative. Because distance, position is the antiderivative of velocity. So distance is some way related to the antiderivative of velocity. And since the distance geometrically is now interpreted as the area under the curve, then the area under the curve seems to have something to do with the antiderivative of the function that defines the curve. That's our geometric introduction to integral calculus. The actual area under the curve has something to do with the antiderivative of the function that defines the curve. Just as the slope of the tangent line has to do with the derivative of the function that defines the curve. Okay? The area under the curve. Now, whereas the derivative, we're going to be interested in, when we take the derivative, we're looking at it at an instantaneous, at just a single point, because it's instantaneous. In order to define the area under the curve, that area is not going to equal anything if we are only looking at a single point. The area under a single point would be 0, because the associated rectangle would shrink to nothing. So we must be talking about the antiderivative over an interval. Okay? The antiderivative over an interval. Okay? And we'll get back into that soon enough in a couple of sections. Right now we're recognizing that there is a relationship between the area under a velocity function and the distance that the object traveled. There's a relationship between those. And we can, in general, be taking a look at how do we find the areas under functions, nonlinear functions. If they're smooth and they're continuous, whatever they are, when is it possible? When is it possible for us to find the area under a curve? We're going to want to define it for right now only over the x-axis and define it within a closed interval. We're not going to want to do this whereby we have any vertical asymptotes, or funny business like that. Not yet. Okay, just well-behaved functions over closed intervals. How do we find their areas? And we already have an idea now. We can choose values within the intervals that we're interested in, values on the curve itself within each interval that we might be interested, and choose that value to be the representative value of that interval. Geometrically, that means that value gives us the height of a rectangle over the interval that we're interested in. And if we increase the number of values that we choose within an interval, so we go down here to the interval a to b, as we increase the number of sample points we choose along the curve, we would increase the number of rectangles. We would also be shrinking the width of each of these rectangles. Okay? And we would be improving our approximation to the actual area under the curve. Let's take a look at the typed notes that I give to you. I'll try to demonstrate this idea with a more generalized region as well. You would not be needing to calculate the area of a region like this, not in this course. And we're going to deal with more simplified models, but this is to demonstrate the idea as well. A two-dimensional region that's a strange shape. How can we find what the area is of this? We ultimately want to know the exact area of this shape, but it's not the shape of anything that we necessarily know. We can start by taking approximating points. Take a couple points, a point from the top and a point from the bottom, a point as far to the left as we can find, and a point as far to the right as we can find. And then draw a rectangle that goes through those 4 points. And here are some possibilities for the curve that I've given. All right, 3 different possibilities. Each one of these red rectangles can be considered to be an approximation for the actual area of the shape. Each approximation varies depending on where the points were selected on the curve. And some of these approximations might be too large. That is, they might give us an overestimate of the actual area. This one looks like it's giving us an overestimate of the actual area because it completely surrounds it. And some might be underestimates, like this one right here. It looks like the area in this rectangle here is an underestimate for the area of the curve. Well, if we have one overestimate and one underestimate, then that means we now have an upper bound and a lower bound for the actual area. And if we can improve our overestimate, like if we can come up with a new overestimate that is not as large as this, and if we can improve our underestimate by getting a larger area that is still an underestimate, right, we can create sequences of areas that should converge to each other. and close in on the actual area of the region. And we can also choose points whereby we sort of get a balance of both, like this rectangle here. This rectangle looks like it has a little bit of an overestimate of the region from a piece like this, combined with a little bit of an underestimate of the region, right? So a little bit of the region goes outside of our rectangle, and a little bit where the rectangle actually goes outside of the region, right? And so we might consider that on some parts on some parts we have underestimate, on some parts we have overestimate, and they kind of cancel each other out, and overall may give us a better approximation. And we're really after the exact area. What's one way that we can improve our approximation? We can add more points, just as we said we could do with the speedometer. We could look at it more frequently. We create more and smaller time intervals then to look over. Okay? So in the same way, we can choose more points along the top and the bottom, okay? And we can create, therefore, more rectangles. And it's the sum of these rectangles, the sum of the areas of these rectangles that we're using as our approximation to the area of the entire region. As we increase the number of rectangles in general, we should expect that we are getting closer and closer to the actual area of the region. Now let's take a look at this as if it was part of a function. If I just take like one quadrant of it, okay, so we can get back to a more basic design. This is something like we would want to approximate the area under within this course. We have an interval from a to b on the x-axis. We have a function up here, f of x, y equals f of x. What's the area of this region? How can we find it? All right, we are developing a geometric process. We have y equals f of x. We can choose sample points along the curve, and they can be at regular intervals. That is, separate those intervals between the subintervals can be of the same width. Like we can make each one exactly the same width. That would be called a uniform partition of the interval a to b, if we made them all the same width. But we don't have to choose the same width. We could have looked at the speedometer at, we could look at the speedometer, let's say at after 1 second, and then look at it again after 7 seconds, and then maybe again after 22 seconds, and then the next time might be after 24 seconds. So we don't have to force ourselves to look at it along a uniform partition, although it may be convenient to do so. It will be convenient to do so if we can. But the point is, we can choose sample points, and for each sample point, that sample point is contained within some interval that is a subinterval of the main interval a to b. Okay, and we draw a little horizontal line then. Right, for each choice of a sample point that we make, we then can draw a horizontal line that stretches over the little subinterval that we selected it from within, and then we can draw vertical lines and create rectangles. The more points that we choose, the more rectangles we'll have. And the more points we choose, the skinnier the rectangles will be, the average width of each rectangle as well. So overall, the areas of the rectangles individually are going to vary depending on the more points that we choose. But the more points that we choose and the more rectangles we have, the better overall approximation we'll get for the total area as we sum up the areas of all those little rectangles. We're going to be summing up a whole bunch of quantities then. Okay, summing up in this case the areas of the rectangles. And the notation that we use to write that we are in a compact form, that we're doing a summation, is the sigma notation. So I'd like to reintroduce you to sigma notation, which hopefully you have seen before, at least in your pre-calculus course and maybe other courses. This is the uppercase sigma symbol, right, from the Greek alphabet, and we use sigma to stand for summation. The quantity underneath is the starting value of the index. In this case, I'm using lowercase I as the index. It doesn't have to be I. It can be, oftentimes it can be K, it can be L. Okay, but we'll start with it just being I for right now. So the number at the bottom is the starting value of the index. The index is always going to be a counting number for this course. So we're going to have I starts at 1, and it's going to count up from there until we reach the number up top. And the number up top right now is n. So let's say I had the number 4 on top. I equals 1 to 4. That means we would be summing quantities, okay, summing quantities in a sequence or a function such that for each of those quantities we're going to input values of the index variable, starting with 1 and ending at 4. And then what we're going to do next, we're going to apply a limit to that in order for us to define what the integral is. This will be defining a definite integral, which is for the next section after this one. What the limit represents for us geometrically is that we are going to be adding together the areas of more and more rectangles. Geometrically, we're saying, like, if we wanted to divide this region up into 4 rectangles, we would choose 4 sample points from the function and have 4 subintervals from A to B. We would subdivide A to B up into 4 subintervals. If those subintervals had equal width, we would call them, again, a uniform we would call it a uniform partition if they had the same width. But if we had 4 intervals, there would be 4 rectangles, so we would have to be summing the areas of 4 rectangles. So that would be a case where we'd write in sigma notation I equals 1 to 4, the area of rectangle I. And we can write that area of rectangle I like a sequence quantity, like A sub I. Okay, so we have A sub 1 plus A sub 2 plus A sub 3 plus A sub 4, where each of those terms in that sequence would be associated with the areas of the rectangles. And if we were to increase the number of points, we would get better approximations to the actual area. Ultimately, we'll get the best approximation and, in the best cases, get an exact area by choosing an uncountable number of points off of the function. This is going to require continuity of the function that we can do this. Okay? And taking the limit as n goes to infinity, then we are taking the sum of an infinite amount of rectangular areas. And each of those rectangles are going to have a positive area. Right? So area is not going to be negative. And it certainly shouldn't be 0. If we were adding up a bunch of zeros down here, it would tell us that the area under this curve is 0, and clearly it's not. So we're going to be adding up a bunch of positive quantities, an infinite amount of positive quantities, and that value that we get out of it is not going to be infinity. We've talked about that idea before. If you add, it is possible to add together an unlimited supply, an infinite amount of positive numbers only, whereby the result of adding all those positive numbers does not give you infinity, but it gives you a finite value. And that's what's going to happen when we do this, right, on well-constructed functions, right, that geometrically are well-behaved, which is what we'll be looking at here in this course. Now, the choice of I'll get back to sigma notation in a moment, but as we are choosing points within each subinterval, or again, I said that you can choose the point to be anywhere within the subinterval. We're going to have 3 main selections, we can say, for us to study within this course of choices we could make within each subinterval. So suppose that I have an example where I've divided this interval from A to B, I've divided it up into 6 subintervals. All right, so we have, and this is not a uniform partition, you might notice also. Some of these rectangles are wider than the others, so it's not uniform. But nonetheless, we've chosen points from the curve. First note, there are 6 subintervals. We have 1 right here, 1 right here, 1 here, 1, and this one right here, which does give us a rectangle of height 0. This one happens to. So we have 6 subintervals associated with 6 rectangles. Even though this one is a rectangle of area 0 here, it's an approximation rectangle, right? And notice the area of that rectangle is an underestimate of this actual region right here. 6 subintervals. How many points did that require us to take? How many sample points do we actually have off of the function, though? Well, for this is the first sample point we have. How do I know this is the sample point? Because that's the value that is associated with the height of the first rectangle. Was this being used as a sample point? It was not, because this is not the height of any rectangle that we're looking at. Take a look, though, at that point at the next image over here. That point, the same point as this right here, over in this image, that point does give us the height of the first rectangle. You see that with these same points along the function here, if we choose the sample points along the function to be at the right edge of each rectangle, right? This point right here is at the upper right edge of the associated rectangle. This point is at the upper right edge of its associated rectangle, right? Right. Then we are saying that we're going to say that we're choosing right endpoints, and the approximation then, that's the sum of all these areas. When we choose the right endpoints, we're going to say we're going to do that approximation by the right endpoint rule. If we choose for each of the sample points to be at the upper left edge of the associated rectangle, so that's the horizontal line emanates out towards the right, so that our sample point is always at the upper left edge of the rectangle, right? Then we are saying that we are choosing left endpoints. Just as we could have selected to look at the speedometer at 12 o'clock or 12:01 or at any time in between. You could think if we looked at the speedometer at 12 o'clock exactly, that would be like taking a left endpoint as our estimate. Looking at it at 12:01 would be like taking a right endpoint for our estimate. And what about if we looked at it at 12 o'clock and 30 seconds, exactly halfway between 12 o'clock and 12:01? We would call that taking the midpoint. So if the sample points that are determining the heights of the rectangles, if those sample points are found in the middle, exactly halfway between the left edge and right edge, we call those midpoints. And again, these are not the only options we have. We could have chosen the points to be anywhere within the subintervals, truthfully. But the three fundamental ones that we're going to look at are choosing right endpoints, left endpoints, and midpoints. So let's take a look at how these compare to each other geometrically. They all of these would give us approximations for the actual area under the curve. Some of these rectangles will give us overestimates. Notice this one here is giving us an overestimate, and so is this one, and so is this one. Some of them will give us underestimates. Notice this rectangle is an underestimate of its associated area because there's a little extra piece of the curve above it. So we might get combinations of overestimates and underestimates. And the midpoint, generally speaking, will give us a combination of the two. It depends on the shape of the curve. Notice that each of these rectangles seem to give us a little bit, right? If you take this rectangle here as a good example, this portion of the rectangle seems to be an underestimate, but this portion of the same rectangle is an overestimate. So it kind of balances the two out. So overall, we'll expect the midpoint to maybe give us a better approximation versus the left or the right endpoint. However, there's a little extra work involved in finding the midpoint. That is, after you've decided how many subintervals you have, and you've subdivided the main interval A to B into that many intervals, you would then need to, with the midpoint formula, you would then need to go within each subinterval and find the location of the midpoint. And that's a little extra work. But you get an extra benefit out of it in that you're going to get a better approximation. Now, speaking more on overestimate and underestimate, as we can observe from any one of these, let's take this as an example. Notice that the function y equals f of x is an increasing function until it gets to this point. If the function is increasing, but we are choosing the right endpoints, just along this segment right here, an increasing function where we choose right endpoints, is it giving us an overestimate or an underestimate to choose right endpoints of an increasing function? And we'll notice here, these three rectangles, all chosen by right endpoints, all in an increasing branch of this function, they all give us overestimates. Does that mean that the right endpoint will always give us an overestimate? Look at these three rectangles here. We are still using right endpoints here, but the function is decreasing over this portion. A decreasing function given right endpoints we will get an underestimate. So if the function is partly increasing and partly decreasing, we can expect to get kind of a balance and a cancellation of some of the overestimates and underestimates from a right endpoint. And and similarly with the left endpoints, notice that an increasing function with a left endpoint, the left endpoint would give us an underestimate on an increasing portion of a function. But the left endpoint gives us an overestimate. The rectangles are overestimating the area if the function is decreasing. The shape of the curve and the choice of where we select the point they have something to do with whether our approximation will be overestimate or underestimate, or a balance of the two. Okay, so in total here, in order to create 6 subintervals of the main interval a to b, in each of these cases, there were originally 7 points that were selected. Not all 7 points were used for construction of those rectangles, but there were 7 points that were selected along the curve, starting with this point right here at A, and ending with this point right here at B. Okay? So I have 1, 2, 3, 4, 5, 6, 7. 7 points are required to create 6 subintervals. All right? 1, 2, 3, 4, 5, 6, 7. There would have to be 7 x values within this interval, and each of those x values are associated with y values along the curve, because the function has to exist here on this closed interval. 7 x values, 7 y values. When you're using right endpoint and left endpoint, okay, then in either of those cases, only 6 of those 7 y values will be interpreted as heights of rectangles. And when you're doing midpoints, you're going to have to, for every 2 consecutive x values, you're going to need to find the average of those 2 to find exactly the midpoint of that subinterval. All right, so if you define the arithmetic mean, the average, you add 2 quantities together and divide by 2. So if this is where x is equal to 1, but this is where x is equal to 3, you would say 1 plus 3 is 4, divided by 2 gives us 2. So halfway between 1 and 3 is 2. That's the extra computation you need to do in the midpoint formula. For each subinterval, you would need to take the average of the x values. Then you don't take the average of the y values, I might add. You find a sample x value, and we're going to label that xi star with the star, the sample x value for each subinterval. And then we're going to evaluate the y value relative to that sample x value. And we're going to call the y value f of xi star. All right, so there's a lot of stuff that goes in here. All right, kind of summarize this in a synopsis down here. To estimate the area under f over a closed interval, we can take the sum of n rectangular areas. Ln, Rn, Mn, those are the left endpoint, right endpoint, midpoint formulas, where n is the number of rectangles. It should be a subscript there. The number of rectangles that have been selected. Okay. For convenience, if possible, we would like to choose a uniform partition. That would be specifically where the width of each rectangle is the same. If possible, we would like to do that. But sometimes it's not possible. Where is it not possible? Again, if you're driving in the car, you could be looking at the speedometer every so often, and you're not required to look at it at regular intervals. It could just be that you happen to look at it when you look at it. And let's take this back to the velocity versus distance. Suppose that you're trying to figure out the distance an object has traveled, maybe a distance that you're watching travel through the sky. If you're able to determine its velocity at various times, but those times might not be uniformly separated, you can still use those velocity measurements to get an approximation for the distance. It doesn't have to be a uniform partition. But if it is a uniform partition, how do you find the width of each rectangle? That is the delta x. Well, you take how long was the original interval from B to A, and you divide that by how many rectangles did we choose to create. That's how you find the uniform partition. Okay, the width of a rectangle in a uniform partition. And this xi star, that is again the notation that we use for the chosen x value within each subinterval. The I, the subscript I, that's our index, like we saw in the sigma notation. Okay. So if I take a look back at the one of these examples right here, for instance, the value of the xi stars would be the x values that then get associated with the associated y values on the curve that then determine the height of the rectangle. So for this right endpoint one, this x value right here would be called x1 star. Okay, because it is the x value for this first subinterval here, the x value that then gets related to the y value, which we can call y1 star or f of x1 star. Okay. And that y value then determines the height of the rectangle for that subinterval. This x value would be x2 star. It is the x star value of the second subinterval. This is the y2 star. It is the y value of the second subinterval. And y2 star can also be written as f of x2 star, right, with function notation. This would be x3 star, x4 star, x5 star, and x6 star, using the right endpoint rule for this example. Over here, this would be x1 star right here, because that is where we are locating the height of the rectangle through the function. So this is x1 star, this is f of x1 star. And f of x1 star is the height of the rectangle. This is x2 star, x3 star, x4 star, x5 star, and x6 star. Okay, now how many x stars do we have? We have exactly 6, because each x star value is associated with a y star or an f of xi star, right? Which would geometrically be interpreted as the height of the rectangles. There have to be as many x stars as there are rectangles, because each x star is associated with some height of the rectangle through the function. Okay, so we choose all these x values. When we've selected how many subintervals to take, by knowing how many rectangles we want, we can get told how many subintervals, how many rectangles. N is the number of rectangles we want. Therefore, we need n subintervals. That means we need to have n plus 1 points off of the function. Like we needed 7 points off of the function. But it was 6 of those points, that is n of those points, that become the star values, right? So there's going to have to be n of these xi star values then. Each of these xi stars are associated with an f of xi star. F of xi star is the height of the associated rectangle. If we multiply the height of the rectangle by the width of the rectangle, which on a uniform partition would be delta x, if we multiply the height of the rectangle by the width of the rectangle, if it was a uniform partition, delta x, this product would then be the area of that associated rectangle. So this is symbolically how we can represent the area of one of our rectangles. In the example we were just looking at, there would be 6 of these rectangles. Okay? Just on that one, there was not a uniform partition, so the delta x would vary with respect to each rectangle in that example. Well, then the area, okay, this is still going off the assumption of a uniform partition, so delta x is the same here. The total area would be found by taking the sum of all of those areas then. The sum of all of those areas. That's using the sigma notation, I equals 1 to n. You would multiply the f of xi stars, which would be the heights, which are then multiplied by the associated width. So each one of these, f of xi times delta x, that is an area. That's a height times a width. Okay? And that should have a star in it right there, an xi star. So this is a height times a width. So this term is an area, and we are summing together these areas. How many? N of them. So we have, if we plug in I is equal to 1, this product would give us A1, the area of the first rectangle. Plug in I equals 2, we would get A2, this is the area of the second rectangle. And so on and so forth until we get to N. So in our example, we would have I equals 1 to 6 of f of xi star, but the delta x was not uniform, so that's something that would have to, it would not condense completely into this sigma form. Okay, we'll take a look at an example where it does. And moving ahead into the next section, and then ultimately into integrals, how do we improve our accuracy? Increase n. If we theoretically push n towards infinity, the larger that n gets, we're going to get better and better approximations. In the sense of a limit, we will approach the exact value of the area under the curve. So we're going to need to be able to take the limit of things such as this as n goes to infinity. All right, let's take a look at a real example here. Let's take a nice continuous function. Here's an example. Approximate the area under the curve y equals x cubed plus 1. Between x equals 1 and x equals 3, that would be giving us an a and a b. We now have an interval on the x-axis to work with, from 1 to 3. Above y equals 0, so that means above the x-axis. That's typical for this course. Okay. By using 4 rectangles. Therefore, the number 4 for this example is the value of n. We're being told there are 4 rectangles, therefore we need to have 4 height, right? We need to have 4 height values. Okay? But how many points are we going to have to subdivide in order to create 4 subintervals from 1 to 3 on the x-axis? We actually would need to have 5 points on the curve. Right? So notice there are 5 points here, 5 x values associated with 5 y values. So from 1 to 3, the first of those points would happen where x equals 1. The last of them would be x is equal to 3. Now let's divide into a uniform partition this interval, okay, into 4 equal width subintervals. So the entire length of the interval is a length of 2. 3 minus 1 is 2, right? This entire length is 2. And if we subdivide it into equal sized widths, 4 equal sized widths, the width of each of those subintervals would be a half. In other words, formulaically, if we take the size of the interval, b minus a, divided by the number of subintervals, which in this case is 4, we get the width of each rectangle if we have a uniform partition. So those subintervals then would be from 1 to 1.5, right here, 1.5 to 2, right here, 2 to 2.5 here, and 2.5 to 3. Now we have 5 points on the curve. There's a point right there, 1 f of 1. Here's 1.5 f of 1.5. Okay, here's the third point, the fourth point, and the fifth point. And depending on whether we choose right endpoints, left endpoints, or midpoints, we won't need all 5 of those for our rectangles, but we certainly needed them in order to do the construction at the beginning here to get the process started. So we can geometrically draw the curve, right? We can plot the points that we're interested in. Okay, we'll start drawing the rectangles when we determine whether we're choosing right, left, or mid. In this first case here, we're doing right endpoint. So for the right endpoint, right, then for each subinterval we choose the point that the representative point to be at the upper right corner of the rectangle. So our first point we would choose here would be this point right here. The value then of x1 star would be 1.5. That is the chosen x value. The star means the chosen x value. The subscript 1 would be for the first subinterval. So x1 star is 1.5. F of x1 star would be what we get when we plug 1.5 into the function. F of 1.5. That would be our f of x1 star. It's the height of the first rectangle. So the height of the first rectangle is f of 1.5. Use the function y equals x cubed plus 1, plug in 1.5, 1.5 cubed plus 1, I get 4.375. So 4.375 is the height of our first rectangle. And the width of that rectangle was 0.5. Got that from delta x, from the uniform partition. Therefore, the area of this first rectangle, the area would be 0.5 times 4.375, or Or the other way, 4.375 times 0.5, you can commute them as well. Right? The product of these two numbers right here would be the area of that rectangle. Now continue the process. The next rectangle, we would have x2 star, the second x value that is chosen. Okay, the second x value that is chosen to establish height. x2 star is equal to 2 in this case. Plug it into the function to find the associated height. That is f of x2 star. F of x2 star in this case would be f of 2, because we're using right endpoint, and f of 2 outputs 9. 2 cubed plus 1 is equal to 9. So the height of this rectangle is 9, and the width is 0.5. Continue the process. x3 star is 2.5 right now. The y-coordinate here is f of x3 star, that's f of 2.5. Okay, so we put that height there. I factored out the 0.5 from here, right, because it's going to be the same width for each one of these rectangles, right? It's constant, it's the same width for all the rectangles, so I factored it out. And finally we have here, this would be x4 star. It is the chosen x value for our fourth subinterval. We plug x4 star into the function to find the y4 star, or f of x4 star, the height of this rectangle. Okay, so that's 3 cubed plus 1, that gives us 28. So 28 is the height of the last rectangle. Okay, so we add up the areas. Okay, 0.5 times each one of these quantities would be the area of one of these rectangles. Add up the areas of the rectangles, we got 29. So 29 is an approximation we have for the area under this curve. Take a look at the picture. Given that this function is an increasing function over this entire interval, and we've selected right endpoints only for this subinterval, did we end up with an overestimate or an underestimate? We ended up with an overestimate. And remember that if the function were decreasing, then the right endpoint actually would have given us an underestimate. You can always redetermine that by sketching a function. You can just sketch a quick curve right now that's a decreasing function and put some right endpoint triangles under it in order to see would that be an underestimate or an overestimate. And if you have a function that is increasing, decreasing, increasing, decreasing, maybe like a sine wave or something like that, right, then you're going to get over different pieces of it, you're going to get overestimate, underestimate. So 29 is an overestimate for the area under this curve. And I mentioned here also that this left, this point right over here at f of 1, leftmost one, was not used in this approximation. All right, if you want to do L4, the left end point with 4 rectangles, we are still doing a uniform partition, so 0.5 is still the width of each one of those rectangles. And what are the heights of the associated rectangles by left end point? We choose the left edge of each subinterval as our star values. x1 star would equal 1. x2 star is 1.5, x3 star is 2, and x4 star is now 2.5. Up here, right, x4 star was equal to the 3, right, at the right edge. But down here, x4 star is actually equal to 2.5. Now the associated heights, notice some of these heights are going to overlap with left endpoint versus right endpoint. Right? We still have the height of 4.375. We still have the height of 9. We still have the height of 16.625. Those are still included. Right? But now when we did the left endpoint, we're also going to include the area of this rectangle right here, right, which is a height determined by 1. 1 cubed plus 1 would give us 2, so the height of this rectangle is 2. So we include that height in there, but we do not have a height, we do not include the height of this larger rectangle here, right, because we're doing left end point. And the interval has ended at 3. We don't extend it out to 3.5. We just, we stop calculations there. So we don't include that extra 28. And looking at the picture here, is this an overestimate or an underestimate? By the left endpoint rule, increasing function, we have an underestimate. And that underestimate is 16. Well, now guess what? The actual area under the curve, if we could get it exact, has now been bounded. The actual area is less than 29, but more than 16. And we know that we can improve our approximation by increasing the number of rectangles. So if we went to, say, increase this to 8 rectangles, that's more work for us to have to do, okay, geometrically, algorithmically, okay, arithmetically. It's more work, but if we increase the number of rectangles to 8 and do right endpoint and left endpoint, we would get another overestimate and another underestimate, but they would be closer to the actual value. So we'd be able to close in on the actual value by increasing the number of rectangles and investigating whether our quantities that we found are in fact overestimates or underestimates, which we can determine geometrically reasonably well, because this function is strictly increasing over this interval. Now to do midpoints, we still started with the same 5 endpoints of the subintervals. We still had the same subintervals. The first subinterval was from 1 to 1.5. Well, what's the midpoint of that? We're not going to take the average of the y values, but the average of the x values. What is halfway between 1 and 1.5? It is 1.25. Formulaically, we say for subinterval from xi minus 1 to xi, right, we would take the sum of the two endpoints. So in this case, for this interval here, xi minus 1, that would be 1, and xi would be 1.5. Why the use of the I? Remember, the I, the subscript I, can tell us which subinterval we're looking at. This here is the first subinterval of interest, the first. So this would be the interval where I would equal 1. So this is saying that you're looking at the subinterval from x sub 0 to x sub 1. Right, x sub 0 to x sub 1. So we're saying x sub 0 or x naught is equal to a, the value at the left. X, right? X naught is equal to a. Okay. And we'll continue to refer to it that way as we move ahead to further define what the definite integral is. We move into the next section. Okay, so we find the midpoint of each subinterval. 1.25, the midpoint between 1.5 and 2 is 1.75. The midpoint between 2 and 2.5 is 2.25, right? Again, calculated by add together the left and the right edge of the subinterval and divide by 2. It's an arithmetic mean. Those 4 mid values, then, those 4 midpoint values are the xi stars for this example. 1.25 is x1 star. 1.75 is x2 star. 2.25 is x3 star, and 2.75 is x4 star. All right, so the star values are changing depending on which rule we choose. And we do the same thing each time with those star values. We plug them into the function itself, which tells us what the height of the rectangle is. The f of xi star values are the heights of the rectangles. So f of 1.25 is a height. F of 1.75 is a height. F of 2.25 is a height. And f of 2.75 is a height, by use of the midpoint rule on this example. Midpoint 4, M4. So we evaluate those heights, and each height gets multiplied by the associated width. We're still on a uniform partition, so I factored out that width since it was the same throughout. And we get an approximation, 21.75. Notice that the midpoint rule has now given us, for each rectangle, we end up with a bit of an overestimate and a bit of an underestimate on the same subinterval. So they kind of cancel each other out. So we get a better approximation for the actual area. In this case, 21.75. And that comes between 16 and 29. It gives us a better approximation. Okay, so we get better results, more accurate results by use of the midpoint rule, but we do have a bit more work to do, and that is in finding the midpoints themselves. Okay, so suppose that we had a velocity. Suppose that we had a velocity function that were described by the function we were just looking at. V of t equals t cubed plus 1. Suppose that that was a velocity curve. Right? Then we just found by use of the midpoint rule, the area under that curve from 1 to 3 is approximately 21.75. Interpret that in terms of distances. Well, the area under a velocity curve, that is, if we take the height of the rectangle again, right? The height is velocity, and the width is time, and velocity times time gives us distance. We interpret this area, therefore, as the distance the object would have traveled. So if we know the velocity function, okay, and we bound it over a time interval, from, in this case, from 1 to 3, and choose one of our approximating methods for that area geometrically, that area under the velocity function over a closed interval of time, that area is interpreted as a distance. So our object here would have traveled approximately 21.75 meters from 1 second to 3 seconds. Over that 2-second interval, that's particular 2-second interval, it would have gone approximately 21.75 meters in distance. Now, although the function may not always be continuous, right? Again, we may be looking at an object moving, and we may not have an actual symbolic function to plug x values into. We may just be using given data points. Here's an example where that may happen. Okay. Estimate the distance traveled over the interval 0 to 8 using left endpoints and then using right endpoints. So let's say we're given different time values. We have the first interval here is from 0 to 0.5. That's a width of 0.5. Then the next one is 0.5 to 1, also a width of 0.5. But the next interval is from 1 to 2, so the width here has changed. Now we have a width of 1. This is not a uniform partition, therefore. So we can't factor out a delta t. It would be a delta t in this case. We can't factor that out. Each one of these rectangles might have a different width. So we should look at the area of each rectangle separately from the others, and then find all those areas individually and then add them together. And here's a look of the function that we could graph. We can only have points. And we can assume that this thing is moving continuously, so we could, interpolate here. We could draw a best fitting curve that tries to get as close as possible to these points. Okay? But it's really just these data points are the ones we have. And we can use those data points then in order to construct rectangles over the subintervals. We want to use left endpoints here. Okay? How many points do we have? We have sample points. We have 1, 2, 3, 4, 5, 6. We have 6 data points to collect. We don't have any other data points to anticipate outside of here. We're not going to extrapolate. How many subintervals can we construct? Well, we can create a subinterval between the x values of these 2 points. That's a subinterval right there, that from 0 to 0.5. That's one interval between these two. One interval between these two, that makes 2. An interval between these two, that makes 3. An interval between these two, that makes 4. And an interval between these two, that makes 5 subintervals that we can construct. There are 5 subintervals. And in each subinterval, we can choose an x star value, right? An xi star. So our choice of x in this subinterval becomes our x1 star. In this subinterval becomes our x2 star, and so on. And we'll have 5 such x stars. And here's our associated widths, not a uniform partition. Okay? Using the left endpoint rule, we choose the left. Right, the left boundary of each subinterval is the x star value for that interval. So with left endpoint, we're choosing 0 as our x1 star. And ultimately then the height of the rectangle is found by interpreting what the function outputs there. So the height of the first rectangle would be 0 by the left endpoint. And then 0.5 would be the second left endpoint. So the height of the second rectangle would be 6.2. The height of the third would be 10.8. The height of the fourth is 14.3, and the height of the fifth is 18.1, and then we're out of left endpoints. We have no more left endpoints that we can use beyond the 18.1 output value. So these 5 velocities are our height values for our rectangles, and each one gets associated with its subinterval's width, which I've calculated here. And then we get our approximation for the area, which we can interpret as distance because we're finding area under a velocity function. So we approximate 114.9 feet. Do we think that this is an overestimate or an underestimate? Look at the function here. We started with left endpoint, starting with this one. Our first rectangle would just be a flat line down here. We'd have an area of 0. Our second rectangle, like so. Our third rectangle, like so. Our fourth rectangle, like so. And if we were to graph a function that interpolates these points, tries to go through these points, it would look like that function is increasing. It's an increasing function. And using the left endpoint, would we expect an overestimate or an underestimate? Okay. Using the right endpoint, take 0.5 as the first star value. So x1 star is 0.5 for right endpoint. Okay, so the output there would be 6.2. So 6.2 is the height of the first rectangle when using right endpoint. First height, second height, third height, fourth height, and fifth height. 20.2 would be the height of the fifth rectangle then. Multiply each of those by the associated subinterval's width, and you get an approximation. And you can see here you have what looks like an overestimate. So we know the actual distance the thing traveled is between these two quantities here. Okay, again, summarizing the process, how you can do it. All right, you can take a look at your homework as well. And let's take a look at the worksheet there as well. You do some approximations there. Your answers will, may vary depending on how you interpret results from the graph. Okay. Let me know if you have any questions on that. Okay, let's take a little look at sigma notation. Okay. All right, sigma notation. The capital A sub I is the area of the ith rectangle, and you are summing them up. Okay, you can write it in this form as well. The xi star, we've talked about that. Okay, delta x, this assumes a uniform partition. What is delta x going to be? It's going to be equal to b minus a, okay, b minus a over n, if we are doing a uniform partition. Right? When we take the sum of these products, this is a height, this is a width. Height times width, area. And we add those together. When we add up those areas, we get an approximation for the actual area. And this is going to be, the output of this is either going to be L sub n, R sub n, or M sub n, depending on whether we have chosen the xi stars to be at the left edge, right edge, or midpoint of each of those subintervals. Okay? Alright, so some sigma notation stuff. More on sigma notation to look at in the following section as we, in 5.2, as we take a look at the definite integral. Closed form sigma notation. Here we go. In general, I equals 1 to 5 a sub I, where a sub I is the name of a sequence here. And then expanded form, this is saying plug in the 1, right? So you get like a1, and then plus a2, plus a3, plus a4, and then plus a5, and that's what it means. So a sub I is really a function. It's a sequence. It's the same as saying we have a of I. It's really a function. But it is a function not defined over real numbers. It's a function here that is defined over the whole numbers only. So it's not a function that we're going to plug 1/2 into, or 2/3, or pi, for instance. We're going to plug values of the index into that function when we're defining it as a sequence. So the input is determining the order of the sequence. Okay? All right, so now if we take I equals 1 to 5 of 2, right? That's like saying that we have some function called a of I, and it is the constant function 2. No matter what value of I we plug into that, we're just going to get the output is 2, because it's a constant function. Right? So, etc., etc. So what is this sum? Okay, the output is going to look like this. 2 plus 2 plus 2 plus 2 plus 2. Right? So that's A1, A2, A3, A4, and A5. Add them all up, what do we get? We get 10. In general, notice here that 10 is equal to, or the value of the constant here, times this number up top. Okay? Which, it also depends on the fact that we started the index at 1, which is what we're doing right now. So in general, if we have the summation I equals 1 to n of a constant, let's say c, okay, all right, where c is a constant, this is going to be c plus c plus c plus c n times over, so we're going to have c times n. Right, where c is a constant. Let's take a look at what if the sequence is not being applied to a constant. What if we did I equals 1 to 6 of I? Okay, that's where we're saying that the sequence is the function a of I is just equal to I. All right, so it's linear. A of 1 equals 1, a of 2 is equal to 2. It's like the function y equals x. Y, f of x is equal to x. So from 1 to 6. So I equals 1, we get 1, and then I equals 2, 2, and then 3, and then 4, and then 5, and then 6. Right? So this is A1, A2, A3, A4, A5, a 6. Let's add these up and see. So we have 6 and 4 is 10, and then we have 5, 3, and 2. Those make 10, so that's 20, and then plus 1 is 21. Okay. So this one's equal to 21. Okay, is there a nice clean formula that we could use for this one? Yes, there is. You know, in the development of that formula, if we rewrite the same sum in reverse, okay, create Gauss with this one, the same sum in reverse, right? Well, these add up to 21, these add up to 21. Well, if we add all these up, 1 plus 6 is 7, 2 plus 5 is 7, 3 plus 4 is 7, 4 plus 3 is 7, 5 plus 2 is 7, 6 plus 1 is 7, right? 7, 7, 7, 7, 7, 7, right? We end up with 7 times 6, in other words, 42, right? So we get 42 here. Well, then the original sequence is 42 divided by 2. Right? What does that have to do with the original quantities that were given? Right? Well, 7 times 6, okay, 7 times 6, we were started with a 6 up here, okay, and then 7 is exactly 1 more than that. So we notice is that if we specifically talk about, all right, here we go. If we have the sum I equals 1 to n of I, there are going to be n of these terms. We're going to start at 1 and we're going to end at n. So it's going to be like 1 plus 2 plus 3 plus 4, on and on and on until eventually we get, first we'll get to n minus 1 and then finally to n. We're going to add all these up. And what's the sum of all that going to be? It looks like it's going to be ultimately, right, we're going to divide this by 2. We're going to take whatever n was equal to, n plus 1, okay, we're going to take n, and then that's going to multiply by n plus 1. That would give us this product, and then we're dividing by 2. That's what it would be. Right? Because we had 1 plus 2 plus 3 plus 4 plus 5 plus 6, right? That was the sum I equals 1 to 6 of I. This is also the sum I equals 1 to 6 I. So if you add those together, you get 42 is equal to 2 times the sum I equals 1 to 6 of I. So therefore the sum I equals 1 to 6 of I is equal to 42 divided by 2. Okay, so n times n plus 1 over 2. Formulas like this you can look at in the the appendix of your book, and there will be more like that to look at in the next section. Okay, this is just reintroduction to what sigma notation looks like. I have one more to show you, as if like what it might look like for you to do a summation when finding the area under a curve. So let's say I equals 1 to 4 of, let's say, I squared plus 2 times 1/4. Okay, so this sort of resembles an I equals 1 to n, f of xi star, delta x, like on a uniform partition. If delta x was equal to 1/4, remember that delta x is b minus a over n, so this could be a case where n is equal to 4, and the interval AB has an overall width of 1. Alright, so we have a uniform partition for this example. Let's expand this, starting with I equals 1. I equals 1, so we're going to get 1 squared plus 2 times 1/4, plus I equals 2, we're going to get 2 squared plus 2 times 1/4, right? And then, let's say I is equal to 3, we're going to get 3 squared plus 2 times 1/4. And then we're going to plug in I is equal to 4, so we're going to get 4 squared plus 2 times 1/4. And yes, we could factor out the 1/4, right? It is uniform to this. So, okay, so the 1/4 comes out, and then I'll open up a bracket here. So what, 1 squared plus 2, that's equal to 3. And then 2 squared plus 2 is 6. And then 3 squared plus 2 is 11. And then 4 squared plus 2 is 18. Okay, so we have 1/4 times this is what? 3 and 6 is 9, 9 and 11 is 20, plus 18 is 38. So we get 38 over 4, which reduces to 19 over 2. So that's what our sum is, okay, from this summation then right here. Alright, so let's see. One thing that could be helpful for us to learn from this one is if we have the sum I equals 1 to n of, let's say, an f of xi star delta x, okay, we can factor out the delta x as long as it doesn't depend on I, which it doesn't. It's xi star and f of xi star, those depend directly on I. But we can factor out the delta x and multiply it then, okay, by the sum of terms that do depend on I. Okay. So we can factor this out if it is not dependent on I. Consider that I is the variable here. I is the thing that is moving. And just as we could factor out a constant when we're doing, for instance, differentiation, if we are taking the derivative of something with respect to x, we can factor out a constant, and it's constant if it does not depend on x. In this case, delta x is constant because it does not depend on the thing that is moving within the summation, and the thing that changes within the summation is I. And as I is moving, as I is changing, delta x is constant because, again, delta x does not depend on I. Delta x does depend on n, and n is a constant. N is the number of rectangles. That's not changing. So for this reason, we can factor out the delta x for a uniform partition. And then so you can take the sums of the heights. You can take the sum of the heights of the rectangles and multiply that sum of heights by the width of the uniform partition rectangles. Okay, so that's a bit of a simplification there. Okay, so that's how you can work with sigma notation. Okay, so we've seen left endpoint, right endpoint, midpoint. We've seen how you can do this with functions that are continuous, whether you have the symbolic function. You know, we can see how we could do it if we had just a graph. Here's a graph right here. Okay, from x equals 0 to x equals 10, and we don't have the symbolic function. Just y equals f of x, here's the picture. By reading values from the graph, use 5 rectangles to find a lower estimate for the area. It's a decreasing function. If it's a decreasing function, and if you were to put rectangles under there, right, for an underestimate, would you choose left endpoints or right endpoints? Make the decision for which one you think and draw how many rectangles? 5. Where's the interval from A to B? 0 to 10. So we're going to start from here and go to here, from x equals 0 to x equals 10. So if you use a uniform partition over this interval, 5 rectangles over this interval, what would be the width of each rectangle? This is B, this is A. So we have A to B, and we have n is equal to 5. So the width of each rectangle would be B minus A divided by n. So you can draw in your 5 sub-intervals here along this axis, and then you can associate the height of each rectangle up to the function. Okay, so I'll start with the first one. Let's say we are choosing right endpoints. We go from 0 to 10, divide that by 5 sub-intervals. Okay, 5 sub-intervals. That means each sub-interval has to have a width of 2. The first sub-interval would be, therefore, from 0 to 2. The next one would be 2 to 4, then 4 to 6, 6 to 8, and finally 8 to 10. So the first subinterval would be from here, x equals 0, to x equals 2 right here. Okay. Now for that subinterval, the xi star should be chosen to be a left endpoint, a right endpoint, a midpoint. Which one? Let's say it's a right endpoint. Let's say it is. Well, that means that x equals 2 will be my choice for the first xi star. So the x1 star is this, 2. If I'm choosing right endpoint, then I trace up to the curve to find the height of the rectangle. As soon as I hit the curve, I plot, that's a point then on the curve of interest, and that point is associated with the height of the first rectangle. That point is now a right endpoint. The y value for that point, which we're going to need to estimate, okay, we're going to need to estimate this, so you round your answer, okay, reading values from the graph. The y value for that point would be the height of the rectangle. So if we take, let's say that that's about looks a little more than 3.5. So let's say I take 3.7 or 3.6, something like that. That's the height of the rectangle. Let's say I take 3.7. Okay, so 3.7 is the height, and the width of this rectangle would be 2 in this case. So the area of this rectangle would be 3.7 times 2, which is 7.4. So that's my first area, rectangular area approximation. And we'll similarly then do that for the other subintervals. So from 2 to 4, the next subinterval, I would choose 4 to give us the right endpoint. The function then gives us the upper right corner of that rectangle, which goes back to here. And the y value there, I would say, is about maybe 2.2. Okay, so 2.2 is the height. The width is 2. 2.2 times 2 is 4.4. So on and so forth, using the right endpoint. Okay, sketch the rectangles that you use. Choose the appropriate sketch. Okay, how about you do it using an upper estimate? Would you choose right endpoint? Choose left endpoint? Okay. And then sometimes you're going to have to choose midpoints as well. That'll be in the instructions. Here you're given a symbolic function, and you're given the interval. Okay, using 4 approximating rectangles, so n is equal to 4. Okay, did you get an overestimate or underestimate? Okay, another symbolic function you can use. Okay, and then you have a couple of examples here, like I already worked through, that are dealing with velocity functions. You might have a table of values. The speed of a runner is increasingly steadily, so we have the velocity of the runner, and we have times at which we looked at the velocity. Is this a uniform partition here? Okay, and that's one question. Okay, whether it is or not, you can still approximate the distance. Okay, find lower and upper estimates for the distance. This also has the step-by-step tutorial here for you. Okay. All right, another one, velocity. Use midpoints to get the most precise estimate. Okay, so that is it for the introduction to this section in this new chapter. We now are we talked about antiderivatives recently. Now we're talking about the area under a curve using sigma notation, sums of rectangles. We get an idea for where this is going. Hopefully, that that we're doing. We're going to be running a limit as the number of rectangles approaches an uncountable number. So we're going to take the limit as n goes to infinity of expressions like this in order to find the exact area under the curve. And as we can see with the example of using a velocity function, the area under the velocity function over a closed time interval would give us the distance, the distance traveled over that interval. And so that gives us justification that there is a connection here to anti-differentiation, because the antiderivative of a velocity function is a position function, and we're finding distance by looking at the area under a velocity curve. Okay, so we get the ideas of integral calculus are coming together for us now. Okay, so try out the homework, check out the worksheet and the type notes, and let me know if you have any questions for discussion. Okay, take care.